Thank you very much. Can you hear me?
Yes.
So first, I would like to thank you to give me the opportunity to present this work. This work is a collaboration with Mingwan Zhu from Zhengzhou University. And most of the things I'm going to present today are related to this publication. So the context of the analysis I'm going to consider today is the following. We already see it several times since the beginning of the day. So we have a degraded data Z. So the degraded data is of size M. It's a degraded version of an original image U bar. And the degradation follows the following model. So A is a linear operator. It can, for instance, model a blur. And you have some additive noise, typically a Gaussian noise. So this is a standard image recovery problem, and we are going to focus on this specific framework in all the analysis. And what is important here is that we assume A to be known. So the standard approach to solve this inversion is to minimize this kind of formulation where you have a data term and a penalization. So the data term is here to ensure that the solution will be close to your observation. And on the other side, you have a penalization, which is here to impose some regularity on your solution. And the parameter lambda here is here to adjust the weight you want on the data term and on the penalization. So it's common. So typically here you have a degraded version, which is blur and noisy of an image. You see that if you do not have this penalization, a standard inversion leads to this kind of result because it's going to amplify the noise. And here it's in the context where you have L2 penalization, and here is in the context where you have total variation, which means that you have an hybrid L1-2 norm applied on the horizontal and vertical finite difference. So you see that depending on the way you select the minimization problem, you are going to improve the recovery. During this period between 2007 and 2010, there are many, let's say, several work dedicated to two kinds of approach in order to deal with image restoration. On the part, you have the synthesis formulation, and on the other part, you have the analysis formulation. The synthesis formulation read like that. You want to find an image to recover, which is expressed as D star alpha, where alpha comes from a minimization problem of this form. So you recognize the data fidelity term. So D star A is equal to U. And so you have the standard data fidelity term, and you have a penalization here. So typically you want to impose sparsity on the coefficient alpha. On the other side, you have the similar minimization problem, but this time the D is not on the side of the data fidelity term, but it's on the penalization side. And you typically have the image, you project it in a transform domain, and you apply, for instance, a sparsity penalization on it. So you know that in the literature, you can find that both problems are equivalent. For instance, D is an orthonormal basis, and for very few examples. But in general, both problems are not equivalent. And in the literature, you can encounter a lot of development made on this context or on this context. Several ways to select a D hat has been proposed, essentially related to the theory of sparse coding and also to the, let's say, X-let theory. With the development of all the wavelets. And on the other side, you have the penalization such as TV, because in the case of TV, D model the horizontal and vertical filter, and the norm is the L21 norm. You also have some non-local total variation. In this case, D is not just the horizontal and vertical filtering, but you can have other kind of filter, and each filter is weighted. You can also have local dictionary of patches. You can have some Asian penalization also. So you have these two frameworks, and you have some comparison between both. Sometimes the synthesis perform better, sometimes it's the analysis. And a key question behind that was also how to solve each of these problems. So just to, before to go to the next slide, the important thing is here that the penalization is often non-smooth. And so in this context, you can't use standard optimization technique. And so you need to have recourse to some proximal based strategy. And in this context, a lot of development in order to minimize this kind of objective function were related to the notion of proximity operator. So here is the definition. So if you have a function f, which is a convex, lower, semi-continuous and proper function, the proximity operator of f is the unique point denoted by prox fx, minimizing this objective function. The interest of the proximity operator is that you have a lot of closed form expression, especially for the L1 norm, which was used in the minimization problem presented before, which is the sub-thresholding represented here. And you also have other closed form expressions that for the L2 data term, where the expression is given here. And you have a large panel of closed form expression that you can find on the Prox repository website. Once we have said that, we also need to say that when you want to compute the proximity operator, you have some closed form expression, but you can also have some more complicated tasks, such as computing the proximity operator of F1 plus F2, or the proximity operator of F composed with a linear operator. And this is the main difficulty in our method. So if we go back to our minimization problem, I think that most of you know that if you want to minimize the sum of two functions, and if one or both are non-smooth, you can have recourse to proximity operator strategy. But here is the list of the standard scheme that you can design to find the minimizer. For instance, if F1 and F2 are differentiable with a Lipschitz gradient, then you can perform the gradient descent. If just one has this property and the other one is non-smooth, you can perform the forward-backward algorithm, which is a gradient descent step followed by a proximal step. And if both are, you can compute the proximity operator of both functions. You can either involve the Piesman-Rashford iteration or the Douglas-Rashford iteration. So here you have a minimization problem. A specific example is the synthesis formulation, and it's the reason why in the literature the first work dedicated to image restoration were also dedicated to this synthesis formulation, because it was quite easy to apply a scheme such as forward-backward to minimize such a criterion, because you have this differentiable term where you can compute easily the gradient, and you have this norm, so typically a L1 norm, for which you have a closed form expression of the proximity operator. So then you perform a gradient descent on the data term and a sub-threshold. The problem is that for the analysis version, that is not anymore true, because you can compute the gradient descent, but then you need to compute the proximity operator of the D, the L1 norm composed with the D. And in that case, you can have some closed form expression, but for very specific D. So the first development were dedicated to forward-backward, and few years later, after the development related to primal-dual algorithm, we were able to deal with analysis formulation. So the reason is quite simple. It's because when you have this kind of minimization problem, so a sum of two terms where one is composed with a linear operator, the design of this primal-dual scheme is the following. You perform also the gradient descent over F1, as you do for the forward-backward. You compute the proximity operator associated to the function H2. So here is the proximity operator of the conjugate of the function, but it's related to the proximity operator of H2 by a simple expression. And then the operator D is going to be computed here and here. And so here are the following iteration. And if you iterate that, the sequence xk is going to converge to the minimizer of this problem. So in this context, using primal dual algorithm, you are able to solve efficiently the analysis formulation. An important thing is that you have an extended version of this primal dual scheme where you have an additional function f3, and you see that the expression is the following. So it means that if you have a look, if f1 does not exist, but you have just f3, here you do not have anymore the gradient descent, and you have the proximity of f3. So in a sense, in our analysis minimization problem, you can either activate the data fidelity term as a gradient or as a proximity operation. So now I have introduced the general context. I can go into the detail about the deep learning framework. So the general framework in standard approach is the following. You have to design the direct activation model. Then you have to design a minimization procedure, the analysis or the synthesis formulation, for instance. You have to design an algorithm. Then you obtain an estimate of U hat, and you should perform this minimization for several values of the penalization parameter, and then you should select the optimal regularization parameter to obtain the final solution. The advantage of deep learning procedure is that you do not have to model properly the direct acquisition, the cost function, the minimization algorithm, and the hyperparameter tuning. You just have nice or existing design of network. You take one of them and you apply it, and you have a good estimation of your final parameter. The point is that by just using some standard deep learning procedure, you can already have very good results, but something which is not really satisfactory is that it's difficult to motivate, it's difficult to see why it works so well. And due to that, a good way to have more intuition on that is to have recourse to unfold algorithm. So let me introduce some notation in the context of deep learning. So we are going to use a database UL-ZL. UL corresponds to the original data and ZL to the degraded one. In the deep learning framework, you want to learn a prediction function d theta. So typically you have d theta applies on ZL, and you want to minimize the distance between d theta ZL and UL bar, so the original image from your database. And you can have some penalization. So the standard way is the linear model. So d theta ZL is theta, big matrix theta times ZL. And in the deep learning procedure, you have non-linear model, which is formulated like that. You have your degraded data, you apply the first weighted matrix W1 plus a bias, an activation function, and you repeated that several times. So one of the main work and the first work dedicated to this unfold iteration are the work by Gregor and Lequin with the network called LISTA. And the idea is the following. So you start from this synthesis formulation I presented at the beginning. So you see that you have A D star in place of H. And so you have this minimization problem where you apply a sparse penalization on the coefficient alpha. Then you perform forward-backward iteration are presented before. So you have a gradient descent step, and then the soft thresholding. It's quite easy from this iteration to see that if you put together these two steps, you obtain this form, and you have minus tau h star z on this side. So here you recognize the weight matrix WK, you recognize the bias BK, and you recognize the activation function eta k. So that was one of the first unfolded algorithm, and in a sense, it's associated to the synthesis formulation. And so the question we ask with Mingguan is it possible to do the same with the analysis formulation and not the synthesis one? So to do that, so we start from the minimization problem in the analysis formulation. We write the Condat-Vũ iteration. So you recognize the gradient descent step here associated to the data fidelity term. You have this step related to the linear operator H. You have the proximity operator associated with the conjugate function of the penalization. And you also have the operator H here. You can see that if you once again gather all these terms together, you obtain this quantity. This term here is this one. The z times tau a star is here. You proceed similarly on this side by replacing xk plus 1 into this term, and so you put this expression into that, and you see that once again you can gather all the terms which are multiplied by xk here, the same for yk here. And by doing this reformulation, you see that you can express one iteration of the Condat-Vũ iteration as one layer of the network, where wk is identity minus tau a star a due to that here. The second component of your matrix wk is minus th star. This component is tau h identity minus 2 tau a star a here. And this term comes from this one. Then you have the bias due to this term and this term. And then you have the activation function, which is split it in two terms. One, an identity term, because here you do not have a proximal step. And here you have the proximal step associated with the L1, the conjugate of the L1 norm. I just would like to focus on something here. You see that H now is lambda D, which means that in our network, the regularization parameter is mixed with the dictionary. So the network we first design is the following. We have a standard network where the parameter to learn are H, tau, and gamma, which mean the step size of the algorithm, tau and gamma, and H, which is the dictionary in our minimization problem, times the regularization parameter. So this is the first network, but in order to improve the flexibility in this network, we decided to replace the H tau gamma by HK tau k gamma k. So the network is very similar, except that we have this modification. Then, in order to have a very simple network, and in order to have like an input only the degraded data, we have some specificity on the first layer, but also on the last layer, which are described in the associated paper. So here we are our network. Then we plug it into this minimization, into this empirical risk function. and the objective is to minimize this quantity. To do that, we have recourse to gradient-based strategy. And the interest by having this formulation is that we are able to, so here is the standard backpropagation procedure. And you can see that each term in this expression has a closed form expression. So everything is also given in the paper. I don't have the time to develop here, but what is nice is that we can re-implement by ourselves with a closed form expression all this gradient descent I have. And here is the first kind of result I would like to present. So I display here on the MNIST dataset some result with some standard minimization problem and the network based on the primal-dual approach. So here is the original image. Here is the degraded one, degraded with a blur and noise. Here are standard method, TV, NLTV, EPLL. So we already talked about all these methods. So they are all analysis formulation. IR-CNN is a neural network where you perform on the first step the deblurring and the second step the denoising, and you alternate both. It's a plug-and-play method. MW-CNN is based on a wavelet transform, and here is the result we obtain. So you can see that we are probably comparable to IR-CNN framework, and we can see better results than other strategies. But even if the results are satisfying, I need to say few more things about the network, which explain why it works so well. So the first thing is the design of HK is of utmost importance. So in our work, we consider several kinds of architecture. The first one is HK being a dense matrix, which means that, for instance, if you have an image of size 10 by 10, you can vectorize it, 11 times 11, sorry, you can vectorize it. And in that case, you will obtain HK of time P times 121. And in that case, I display a H, which is of type 10 times 121. In that case, you have coefficient everywhere, and the L0 norm of this matrix is of this order. You can also have other kind of matrix, such as block sparse matrix, inspired by the local patch dictionary. So in that case, you have filter, so several filter at each location, and you translate it of few pixels. And you see that here is filter of size 5 by 5. We have at each location 5 filter, and we strip them every 3 pixels. In that case, you obtain a matrix HK of size 45 times 121, and the number of non-zero coefficient is of the same order than for the dense matrix. So you have different kind of configuration, and the result then will be probably different. So it's what we want to have a look on it. I would like just to mention something else. You see that this dense matrix and block sparse matrix are related to what is called fully connected layer and convolution layer, except that in our case, WK has a specific form. It's not just a WK being either a dense or block sparse matrix, but the WK already has a structure. And inside this structure, we have dense or block sparse matrix. Yeah. So here it's different kind of filter. This is the dense matrix, and this is some block sparse matrix. And here are the associated performance. We can see that the more you have row in your H, the better are the performance. This is in PSNR, this is in SSIM. So that is for a global matrix, a dense matrix, and that is for some block sparse matrix. And you can see that for the same number of rows in your matrix, the block sparse matrix perform better, probably because the coefficients are much more well identified. Then another thing we tested is to combine some filter, and that was the way to obtain the better performance. So typically we have here one filter, the combination of two filters of different size, etc. And the last one is a block sparse filter composed with a dense filter. And here we increase the performance. In the following, we are going to focus on this one. So when you will learn on MNIST dataset, with blur image and Gaussian noise, you obtain this kind of filter for a dense matrix, HK, and for a block sparse matrix. And here are more quantitative results comparing the state-of-the-art method and the proposed network on MNIST dataset for different kind of blur, different kind of noise. Most of the time on MNIST, we outperform the state-of-the-art method. But I would like to insist on something, which is we propose, in a sense, two networks, one which is called partial, the other one which is called full. The partial one is when you fix one of the parameters, so one of the step size of the algorithm, in order to satisfy, if you want the convergence of some algorithm, you need to ensure some condition between the step size, the value of the norm of the involved linear operator. And when you fix one of these parameters like that, you see that the performance are not as good at all. And so it's important to let the network learn all the parameters if you want to have good performance. So here are some visual results on some more complex data sets. So here it's for BSD dataset. So you see that we are very comparable to state-of-the-art. However, when we do more systematically data analysis, you see that we can still outperform sometimes the state-of-the-art method, but not always. At least we are comparable. And I would like just to finish with this alternative, which is a proximal activation of the proposed Deep Primal-Dual Network, where this time we replace the gradient descent by its proximal activation. And we can see that we can design similarly a neural network. We can do all the computation and you have a closed form expression. The main difference is that the neural network is a bit different. You have this additional matrix GK here. And here are the associated results. We perform sometimes better, but not systematically. I would like to finish on a remark about robustness, as it was explained in the previous talk. And I would like to maybe motivate and explain why this kind of unfold algorithm should be more robust. In order to understand that, we could go to the article by Condat and Pesquet, a recent one, where first they prove that most of the activation function are proximity operators. And another interesting result, which is simplified for the study I presented today, is that if WK, bounded, it's linear operators, BK just a vector as we have, and eta K are proximity operator, then our neural network, which is the combination of TK, where TK is expressed like that, this model allows to derive tight Lipschitz bond for feed-forward neural network model in order to evaluate their robustness. And especially, you have this relation, so d theta x plus epsilon minus d theta x, which is lower or equal to theta times the norm of epsilon, where theta, most of the time, is related to the norm of the weight matrix. They derived a tight bond. But something which is important to notice here is that, as we explain, when we unfold the algorithm, most of the things that are included in W is when you do not compute a proximal step, because if you have a proximal step, the proximal step is included in the eta case. So a way to reduce the theta, and so to increase the robustness, is to reduce the norm of W. And in this sense, the more proximal steps you will do, normally the more robust you will be. So to conclude, we design several deep primal-dual net comparable to state-of-the-art method. We have a closed form expression for all the backpropagation procedure, and each step of the global procedure is controlled. The point is that on MNIST, we work very well. I think for more complex data set, we need to still improve our performance, especially all the code we have is in MATLAB, so we don't use the existing toolbox to do that. And to deal with larger data set, we still need to do improvement, but the first results are quite satisfactory. And further investigation are needed to be to evaluate the robustness. Thank you very much. So maybe just to conclude, we can see on this scheme that during several years, we have the design of the model, so the objective function, then we have all the development on sparsity and proximal algorithm, and now we have deep learning, and each step is very interesting because you continue to improve model with the development on sparsity and proximal algorithm, and also probably deep learning because of everything which was discovered before. Thank you very much for your attention.
Okay, thank you very much for this very nice talk. I was wondering, are there any questions from the audience?
May I ask one?
Yes.
So maybe I missed this. So the number of iterations, I think it was capital K on your slide. So how many iterations do you typically choose in your training?
Yes. So the number of we agree that it's the number of layers, not the number of iteration of the
number of layers.
The number of layers. It depends. When you have MNIST, something like 10, and if you have so probably I wrote it on the BSD. I wrote it here. On the BSD is 20, because if you sorry, for MNIST it was 6, and for BSD it was 20, because if we restrict to 6 layers on BSD, it does not work. It's like if you have more complex data, you need more layers. The other thing is that I'm quite sure that the way we design the filter could be improved on the BSD data set. So, but still, I think K equals 6 is not sufficient for such complex database.
Mm-hmm. Okay, so, and also, I mean, this would compared to the model-based methods that you've shown for comparison, this is like a huge gain in conversion speed, right? So, I mean, for them, you would use many more iterations.
To which method?
I think you showed, I don't know, TV, it's for comparison or so. Like,
yes.
So typically, I mean, in my understanding, like these ideas of NIST or so, like, are also there, like, to improve the conversion speed of the classical algorithms, like, because only a few iterations are needed. So that's the
yes, in a sense, it's true. So it means that we use exactly the same scheme. We just consider some variability in the parameters, and it's all. The point is that we perform better because we have this learning strategy in each layer. If, for instance, we fix H to be the horizontal and vertical filter, probably we will need less iteration than the standard procedure because we will learn efficiently the step size of the algorithm. But probably in 20 iteration, we'll not reach.
Yeah.
the result. I'm not sure I understand. I answer correctly to the question, but
I think so. I think so. Thanks.
okay. Okay.
Okay, so Laurent also has a question.
Yes, thank you very much, Nelly, for this very nice presentation. I have a question. I'm not 100% sure that it makes sense, but let me try. So, as far as I remember, in the algorithms, such like Primal-Dual algorithms to solve convex optimization, there are a lot of several additional interpretation for the convergence of those algorithms, and also we have things like, if I remember well, the primal-dual gap that can be analyzed during the iteration. So there are a couple of quantities that are associated with those algorithms. So my question is, if you unfold such algorithms, what remain in the unfolding procedure that can still be considered and studied that existed before the unfolding? So I don't know if you see exactly what I mean, but so is there any possibility to analyze, for instance, a kind of progression through the network of something that will be similar to a primal dual gap or other quantities?
Okay, so I think the answer is related to one of my last slides. So this is, from my point of view, an important result, because it says that if you are able to design your network like that, where eta k is associated with the proximal operator, which is a 1/2 averaged operator, then you have some nice property of the network, and the choice of the WK will impact the robustness. So in an instance, if you are able to say that your network eta k is a proximal, it's a proximal operator, then you have this kind of guarantees. And maybe I'm wrong, but my feeling is the following: when for instance, you do IR-CNN. For IR-CNN, you are going to perform, you minimize a quadratic problem, you obtain the solution, then you plug it in a denoising procedure, and you repeat that. In a sense, we do, in a sense, some similarity. We have some deblurring, then the proximity operator, but it's more simple. And so it fits more easily this framework. And so computing this robustness bond is easier in our case. So I think we can benefit from this theory in order, which is related to alpha average operator, and the alpha average operator are the theory allowing you to show the convergence of most of the forward backward primal dual algorithm, etc. And so I think it's a way to guarantee some robustness on the network. I don't know if I answer completely.
Yeah, but my question was quite open, so. And that robustness result here, could it be equivalently interpreted like a kind of non-expansivity result or something like that for the global?
Yes, maybe. I'm not 100% sure. Maybe what is in their paper, what they propose, but actually it's not really easy to compute, is that they propose a tighter bond for this theta, because in the literature you have a lot of paper providing some bond for this theta which are not really tight, and so you have a tighter bond in this paper, but it's a bit more complicated.
Okay.
But if you do not have a tight bond, then you can't have a tight robustness.
I see. Okay, thank you very much.
You're welcome.
Okay, are there any other questions? No. So let's thank Nelly once more while we switch screens. So.